Ladies and gentlemen, over the last 2 days we talked about the probability of events where only one thing was being done. You were rolling a die one time, you were spinning a spinner one time, you were drawing a single card from a deck of cards. We are going to start talking about multiple events being performed and generating a probability of that event turning out the way you want it to. Today we got counting principle, sample spaces, and probability. This is chapter 15, section 7. A compound event is an event consisting of two or more activities. You roll two die, like you're playing craps in Vegas or something like that. You take two cards out of a deck of cards. You pull a marble out of a bag, then you reach in, you take a second marble out. You reach in, you take a third marble out. That would be an example of a compound event. Alright, each events happen independently of each other. So if I draw a card out of a deck of cards, put that card back in, I pull another card out, the card that I pulled out the first time has absolutely no impact on the chance of getting the same card or any other card on that second pull. So the example we have here, rolling a die. You roll a die and then you flip a coin. They have absolutely nothing to do with each other. However, you could get like a 3 on the die and a head on the coin, or you could get a 2 on the die and a head on the coin, or you could get less than 4 on the die or a tail on the coin. These things can happen, so we're going to learn how to map that out. There are 3 ways to show the possible outcomes that can occur when you do that. Something called a tree diagram. Now these are kind of like part 4 Regents questions where you'd have to draw a tree diagram showing the outcomes of a compound event. You could list them as ordered pairs, or you could graph them. Graphing is not that popular, but it is incredibly well organized, and it only works for 2 events. So if there's 3 or more events, you can't graph them. That would require 3D graph, which we do not have the capability of doing on the Regents because we don't have computer technology to use on the Regents. Alright, a tree diagram. You have 4 flavors of ice cream. You have 2 toppings. How many combinations of sundaes are there? The counting principle says to figure out the total number of outcomes, all you need to do is multiply the number of ways to get a flavor of ice cream times the number of toppings. There are 8 total outcomes. For example, you could have vanilla with sprinkles, you could have vanilla with Reese's Pieces, you could have chocolate with sprinkles, chocolate with Reese's Pieces, strawberry with sprinkles, strawberry with Reese's Pieces, Napoleon. I'm very creative with my ice cream, aren't I? Napoleon with sprinkles, or Napoleon with Reese's Pieces. That would be an example of a problem like this. Alright, well the first way to show this is with something called a tree diagram. So there are 4 flavors of ice cream. So here's what we do. We start from the root of our tree and we come up with 1, 2, 3, 4. So say I've got my vanilla, chocolate, strawberry, and Napoleon. And then I have my toppings, which are sprinkles, Reese's Pieces, sprinkles, Reese's Pieces, sprinkles, Reese's Pieces. Oh, a little bit of a mistake there. And then I could have Napoleon, sprinkles, or Napoleon, Reese's Pieces. Now if I take my highlighter pen here and I trace these, you can see if I can make my line bigger. We're going to get our trace on. There are 1, 2, 3, 4, 5, 6, 7, and 8 outcomes represented here. 8 total outcomes. And you get to the outcomes by going from the trunk down the branch, keep following the branches till you get to basically that leaf on the end. That is vanilla with sprinkles. And of course if I went over here and went down this branch, strawberry with Reese's Pieces, and there's my leaf at the end of that branch. And that's how you come up with all of the different outcomes. So highlighted here is an example of a tree diagram. We can list the ordered pairs in something called a sample space. This is actually what happens with if you follow every branch. So vanilla with sprinkles, vanilla with Reese's Pieces, chocolate with sprinkles, chocolate with Reese's Pieces, strawberry with sprinkles, strawberry with Reese's Pieces, Napoleon with sprinkles, Napoleon with Reese's Pieces. And if we just go through here, you'll notice 1, 2, 3, 4, 5, 6, 7, 8 total outcomes. When we do a sample space, we write it in set notation, as you can see here, and we put curly brackets on it because it's in set notation. The tree diagram and the sample space show exactly the same information. Exactly the same. They're no different. You just have a preference one over the other. Or maybe the directions will tell you. Alright, graphing ordered pairs. This is kind of weird looking, and once again it only works for 2 outcomes, so most people do not really use this. Here I have vanilla, chocolate, strawberry, and Napoleon. Here are my sprinkles. Here are my Reese's. So I have vanilla with sprinkles, I have vanilla with Reese's Pieces, chocolate sprinkles, chocolate Reese's, strawberry sprinkles, strawberry Reese's Pieces, Napoleon sprinkles, and Napoleon Reese's Pieces. So this is your graphing ordered pairs, and I'd have to of course label this. This would be ice cream, this would be toppings. So you're making like a little graph. It's kind of weird. You see them occasionally, but not very often. But once again, 1, 2, 3, 4, 5, 6, and 7, and 8. 8 different outcomes. They're all listed there. Okay? So you have to have the ability to create a tree diagram, to list a sample space, and to do one of these delightful graphs. The counting principle for compound independent events. Multiply choices for each group of possible outcomes to get the total possible outcomes. Total ways of combining or total combinations, etc. So in our last example, there were 4 flavors, 2 toppings, led 8 possible outcomes. How about when we have 3 pairs of pants and 4 shirts? This is going to give us 12 outfits. Well, I can't use the highlighter. It's too chubby. That's just being silly. Toss a coin 3 times. How many possible outcomes? Well, when you toss a coin, you could possibly get head or tail. So there's 2 outcomes for the first flip. There is 2 outcomes for the second flip. There is 2 outcomes for the third flip. 2 times 2 times 2 would be 8 total outcomes. Draw a tree diagram for choosing an outfit. Alright, well, we have outfits from 3 pairs of pants. So I got pant 1, pant 2, and pant 3. 4 shirts. Shirt 1, shirt 2, shirt 3, shirt 4. Shirt 1, shirt 2, shirt 3, shirt 4. Shirt 1, shirt 2, shirt 3, and shirt 4. And there's your tree diagram. Okay, starting from the trunk, we have branch 1, branch 2, branch 3, branch 4, 5, branch 6, branch 7, branch 8, branch 9, branch 10, branch 11, and branch 12. So how many outcomes? Just like we saw up here, there are 12 branches, which means there are 12 outfits. Alright, counting principle and probability. You can apply the principle to probabilities. The probability of rolling 2 5s on a die. The probability of rolling a 5 on a die is 1/5. I'm sorry, what am I thinking? There's 6 sides to a die. It's 1/6. So if I want to roll 2 of them, the probability of rolling a 5 the first time is 1 out of 6. The probability of rolling 5 the second time is 1 out of 6. And we multiply them together. 1 out of 36 is the probability of rolling 2 5s. Now, you can make a sample space of this, and I'm not going to do the whole thing, but it's in your textbook. 1, 1, 2, 1, 3, 3. Well, that's not the right way to do it. There we go. 3, 1, 3, 4, 1. Trying to think of too many things at once here. I got to focus. Focus. 5, 1, and 6, 1. So this is all just the values for the first die changing. You'll notice 1 stays the same. Then we go over here. Alright, and if we filled in this whole thing, there would be 36 total. And here, down way the heck down here, is going to be your 5, 5. So there's only one of them out of 36. The counting principle obviously is much faster than making a huge table. I'm sure you're already sick of watching me draw it, and I only have, 11 of the 36 elements drawn in here. So multiply the individual probabilities together will give you the total probability of the event. Alright, we're done. Have a wonderful evening. We're going to do page 613 tomorrow. I can't wait to see you tomorrow. Have a great night.